Pre-Calc. Today we're going to talk about probability of compound events. So that is more than one event. So you're taking more than one action. You're just not reaching in and getting one marble, or you're not just reaching in once and grabbing a group of 3 marbles. You're taking more than one action. So if we're looking at the probability of 2 independent events, so an independent event is the event is not affected by the previous event. So I'll show you what I mean by that. If we're talking about using a standard deck of playing cards, and we're supposed to find the probability of selecting a spade, then putting it back, and then selecting a face card. So we're talking about what is the probability of a spade and a face card. Okay, so and let me say that a little different. It's a spade and then a face card. Okay, so first of all, when we're talking about multiple events, we're going to multiply them. So we're going to multiply them. What's the probability of a spade? So how many spades are there? There are 13 out of how many total cards? There are 52. So that is just the probability of a spade. The probability of a face card, well, how many face cards are there? There are 12 face cards. How many total cards are there? There are 52. Now, this is an independent event. And the reason it is independent, so I'm just going to write that, it's independent, is because we replaced it. When we picked the face card, it was not at all affected by the fact that we pulled a spade in the first place, because we put the spade back. So then there's still the same deck of cards. There's still 52 cards in the deck. So that this is why that's called independent. It's because we replaced it, that it's independent. So I can go ahead and do 13 times 12. I can also reduce these. It makes it a little smaller. So 13 over 52 reduces to 1 over 4. This reduces to 3 over 13. And remember, when we multiply, we go straight across the top. So 1 times 3 is 3. 4 times 13 is 52. Okay? All right. Another example of an independent event. It says, of our first 42 presidents, 4 were members of the Whig Party. I'll highlight that. 4 were members of the Whig Party. 7 were born in Ohio. Find the probability that a president selected at random will not be a Whig, but will be from Ohio. Okay, so we're kind of, will not be a Whig. So I'm going to put, this is the probability that they're not a Whig, and they're from Ohio. Probability that they're from Ohio. So these are the 2 probabilities that we're looking at. So the again, when we're talking about the one event is that they're not a Whig, the other event is that the probability that they're from Ohio. Now, does their political affiliation have anything to do with the state that they're from? No. The one does not affect the other at all. So because not being a Whig has nothing to do from being Ohio, these are independent events. Okay? So, probability that they're not a Whig. There are 38, so if we do 42 minus, let's see, 42 minus 7, I'm sorry, 42 minus 4. So there's 38 that were not Whigs. 38 are not Whigs out of a total of 42 American presidents. We're going to multiply that by how many are from Ohio. There were were 7 born in Ohio out of 42. Okay, so this is not awake times all those from Ohio. And this time, because we're talking about the one and together with the other, the one and the other, we're multiplying them. So if we reduce 38 out of 42, this is 19 out of 21. Just reduce that first. And 19 times 1 is 19. 21 times 6 is 126. Okay, so I know on the last one, we didn't reduce it. These are pretty big numbers, and it's pretty easy to reduce. So, of course, you can always change it to a percent by doing the top number divided by the bottom number. So just a reminder, when we're talking about and problems, because this, if we rephrase this, the probability that it's not awake and they're from Ohio. This one is a spade, and then it's a face card. If we're talking about and problems, we are multiplying. In this case, they were both independent. Now, dependent, it means that the one event does affect the next event. The event is affected by the previous event. So if we look at an example of that, Hugh has a bag that contains 4 red, 6 green, and 3 brown candies. He randomly chooses 3 candies from the bag. Okay? Are these independent or dependent? Well, in this case, they are dependent. Well, why are they dependent? Well, it is because each time you draw, there is less candy. Because each time you draw, there is less candy. We did not replace it this time. Okay? We just kept picking. So this is the probability that we get a brown and a brown and a brown. Well, the probability that the first one is a brown, the probability the first one is a brown. Well, we start out with 3 brown candies. So there are 3 brown candies. If we go 4 plus 6 plus 3, we get 13 total. Okay, so that's the probability, but we're going to keep that one, right? Okay, so now how many brown ones are left? Well, we already have 1 brown one in our hand, so there's 2 brown left. How many total candies are there? 12. For that last brown one, there is 1 brown candy left. How many total? There is 11. Okay, so this is the first one, the 3 brown. This is the second brown. And this is the last brown there. So I can either just do 3 times 2 times 1. Maybe I'll just do that. We'll do 3 times 2 times 1, which is just 6. And then we have 13 times 12 times 11, which is 17, 16. So we can leave it like that. Or if we reduced it, we could divide the top by 6 and the bottom by 6. 1 over 286. All right. You could do this as a combination too, because really, if you think about it, what difference does it make if you pick, one M&M, another M&M, a third M&M, or you just grab a group of 3? So we could have done it this way too. Out of 3 brown M&Ms, how many ways can we pick a group of 3 brown? And then out of 13 total, how can we pick any 3? And that would also come out to be 1 over 286. Okay, so we could have done it that way as well, because it doesn't really matter if we're, picking one, a second, and a third individually, or if we're taking group of 3. Now, when you replace it, like we did here, we replaced the card. You cannot do combinations for those. All right, so those were and problems. Whenever we talk about or problems, so these are or problems, we talk about mutually exclusive or mutually inclusive events. A mutually exclusive event is events cannot happen at the same time. There's no overlap of events. There's no overlap. Okay, so I'll show you what I mean here. It says Gina has 6 pennies, 4 nickels, 5 dimes in her purse. She takes 1 coin from her purse. What is the probability that it is a nickel or a dime? So first of all, whenever we have an or problem, we're going to add probabilities. We're going to add probabilities. So what's the probability it's a nickel or a dime? The probability of a nickel and the probability of a dime. Okay, so this is what we mean by mutually exclusive. Mutually exclusive. It means there's no overlap. So this is mutually exclusive because a nickel can never be a dime, right? I'll show you a case where there is overlap shortly, but a nickel can never be a dime. So in this case, we just take the probability of a nickel. So there are 4 nickels and 15 total coins. If we go 6 plus 4 plus 5, we get 15 total. All right, and probability of a dime, there are 5 dimes out of 15, so the probability is 9 out of 15. Okay, we could reduce that, of course, divide the top by 3, bottom by 3, and get 3/5. So that is mutually exclusive. There is no overlap. If we're looking at mutually inclusive, there is overlap. Events can happen at the same time. Okay, so for example, in a particular group of hospital patients, the probability of having high blood pressure is 3/8. The probability of arteriosclerosis is 5/12, and the probability of having both is 1/4. So first of all, determine if they're exclusive or inclusive. Well, in this case, they are inclusive. And the reason they are inclusive is because there's overlap. Some with high blood pressure, also have arteriosclerosis. Hopefully I'm saying that right. Sclerosis. So there's overlap there. Okay, it's not that you just have high blood pressure or you have arteriosclerosis. Sometimes you can have both. So in this case, we have to subtract the overlap. So high blood pressure plus arteriosclerosis minus the overlap. So the overlap is all the people that have both. Okay, so high blood pressure, that probability, there are 3/8 of the people have high blood pressure. Arteriosclerosis, that probability is 5/12. So 5/12 have that. And now how many people have both? So this is the overlap. And that is 1/4 have both. All right, first we have to find a common denominator. The smallest number they all go into is 24. 24. When we add and subtract fractions, we have to do that. So 3/8 is equal to 9/24. 5/12 is equal to 10/24. 1/4 is equal to 6/24. So I'll just put that in the same color just so we can see that these are the equivalent. But then if I add 9 plus 10, I get 19, minus 6, I get 13 over 24. So what's the probability that they will have high blood pressure or? So remember with or problems, then I erased it. When we have or problems, we're going to add. So that's why we're doing this adding here, adding or subtracting. We don't multiply. But because there is overlap, some people have high blood pressure, also have arteriosclerosis, we have to subtract that overlap. So that's the difference between inclusive and exclusive. All right, so let's just do another one that has here some combinations in it. So there are 6 children in art class, 4 girls and 2 boys. 4 children are chosen at random to act as greeters for an art exhibit. What is the probability that at least 3 girls are chosen? So at least 3 girls means that really we're talking about the probability of 3 girls. Remember that they're picking 4. So it says 4 children. So if there's 3 girls, that means there has to be 1 boy in that group. But because it says at least 3 girls, that's 3 girls and a boy, or the probability of 4 girls. So we want to think, is this inclusive or exclusive? Well, is there ever a group of 3 girls and a boy that is also a group of 4 girls? No, it's one or the other. So that's why this is mutually exclusive. Mutually exclusive. We can just write exclusive. Okay? Because a group of 4 girls cannot also be 3 girls and a boy. So probability of 3 girls and a boy. Now remember, this is combinations because it's a group. So out of 4 girls, how many ways can we pick 3 of them? And then out of 2 boys, how many ways can we pick 1? And that's out of how many total ways can we pick 4 of any. There's 6 total children out of, and we're picking a group of 4. Okay? And we're going to add that together because it is an OR problem. An OR problem. Remember, we're going to add. So how many ways can we pick 4 girls? So out of 4 girls, how many ways can we pick 4? Out of a group of 6 of any kids, how many ways can we pick 4? Oops. 3. There you go. All right. So if we calculate this here, 4C3 is going to be 4. 2C1 is going to be 2. And 6C4 is 15. This is 1. This is 15. So 8 over 15 plus 1 over 15 ends up being 9 over 15. Or we can reduce it 3 to 5. Now remember, if that's the probability, now remember if we wanted to do odds, it would be 3 over 2, because remember 3 over 5 minus 3 is equal to 3 over 2. And again, so just kind of a side note, if we wanted to do odds, we could add that as well. All right. So once again, whenever we have an OR problem, we add. So whenever we have an OR problem, we want to add those, okay? And then if there's any overlap, we subtract them. There's no overlap. This was exclusive because there can never be a group of 4 girls that is also, that same group is not 3 girls and a boy. It has to be one or the other. We took all the ways it could come up, 3 girls and a boy. Girls and a boy, that's all the ways it can come up that way. And it was added to all the ways it can come up 1 girl, or 4 girls. It's only one way. And that was over the total. So of course, remember with the total, that denominator stays the same when we add those together. All right, so those are compound events. So big picture, when it's an OR problem, you add it and you want to think, is there overlap or not? Is it exclusive? There's no overlap. You know, the one can never be the other. Or is there overlap or no overlap? Whereas when we talked about some of these earlier, these were more and problems. So that was when we were talking about an and problem. What, you know, not a wig and from Ohio, getting a brown and a brown and a brown. It was not a brown or a brown. It's a brown, then a brown, then a brown. In that case, you multiply them and you want to think, are they independent or dependent? So a lot of information, but those are compound events.